Hello everyone. In this video tutorial, we are going to simulate a flux flow reactor involving a catalytic reaction in Aspen HYSYS. So this is the problem statement. Styrene is produced by catalytic dehydrogenation of ethyl-benzene at temperature starting from 630 degrees C and pressure slightly above the atmospheric pressure. So this is the main reaction where ethyl-benzene is converted into uh, styrene and hydrogen. This is a reversible reaction. At the same times, two side reaction also occur where ethyl-benzene is converted into benzene and ethylene. And in another reaction, ethyl-benzene reacts with this hydrogen which was produced by this reaction, and the products of this reaction where ethyl benzene reacts with hydrogen. It forms toluene and methane gas. So these are the rate equation of the above equations. So these are the rate equation of these reaction, and R1 is the rate equation of this catalytic dehydrogenation reaction. This is K1 PEB. K1 is the reaction constant. PEB is the partial pressure of ethyl benzene. 1 over Ke PST PH2. Ke is the clearing constant. PST is the partial pressure of styrene, and PH2 is the partial pressure of hydrogen. So you can actually say that this K1 PEB is the rate of forward reaction minus K1 by Ke PST PH2 PST and PH2 is the rate of reverse reaction divided by 1 plus KST PST. So this K is actually a constant, and ST is the styrene. So this constant is based on the styrene, and PST is the partial pressure of the styrene. This is how we can calculate the rate of first reaction. Similarly, the rate of second reaction is given by R2 is equal to K2 PEB. PEB partial pressure of ethyl benzene, and the rate equation of the third reaction is given as R3 is equal to K3 PEB. You can see that the rate of the third equation is independent of the hydrogen. Okay, this K1 can be calculated using the Arrhenius law, A1 exponential minus E1 by RT. The values of A1 and E1 are given. Similarly, okay, this K1, this is the K1 which can be calculated using this expression, and when we multiply this K1 here, this will be K1 PEB and this will be K1 by KE. So we call this K1 by KE as a K1 dash, and it can be calculated using this expression. Just put the expression for K1, which is this one, and put the expression of KE. Just replace this A1 with AE and replace this E1 with EE, and we have this expression for calculation of K1 dash, which is actually uh, the ratio of the K1 to KE. So this is the final equation. K1 dash is equal to A1 dash. A1 dash is actually A1 by E. My A1 dash exponential minus E dash by RT. So E dash is E1 minus EE. So this is how we can calculate this term, and this A1 and E and KST, the values of these parameters are given. Similarly, this K2 can be again calculated using the Arrhenius law, and we are given all the required values, the values of A2 and E2. And for the reaction 3, again K3 can be calculated using Arrhenius law, where the value of A3 and E3 are given. So ethyl benzene and water steam enter the multitubular reactor. This is actually a multitubular flux flow reactor, and the mole flow rate at the mole flow ratio of 10 to 1. That means that if 10 mole of steams are entering, 1 mole of ethyl benzene is entering. So in our case, the flow rate of ethyl benzene is 15 kilomole per hour. The steam flow rate is 150 kilomole per hour. The reactor has 500 tubes, and the internal diameter is 6 centimeter. The wall thickness of the tubes are 5 mm, and the length of each tube has a length of 4 meter. And these tubes are filled with the catalyst particle. Uh, they are spherical in geometry, and the diameter of the particles are 5 mm, and the tube wide fraction is 0.45. That means that 55% of the tubes are filled with the catalyst particle. So initial temperature of the feed is 630 degrees C. That means that the feed is entering into the reactor at 630 degrees C, and the initial pressure is 137.8 kilopascal. We are asked to use Aspen HYSYS and calculate the composition, temperature, and pressure profile along the reactor length. That means that calculate the composition, that when the feed move along the reactor, so how the composition, the temperature, and the pressure change. And we are also asked to calculate the selectivity, uh, conversion of ethylbenzene, and selectivity of the styrene if the reactors is working at adiabatic conditions. So open Aspen HYSYS, double click on new, and here is the Aspen HYSYS window. The first step is to add the components. So click on add, and we have to add the components. The components are hydrogen, H2, and H2O is, and so this is water. Double click on this, and it is added. Ethyl benzene, ethyl benzene. This is ethyl benzene is added. Similarly, add the methane as well, and ethene or ethylene. Double click, and it is added. Also add the styrene. Double click on the styrene, so styrene is also added, and toluene and benzene. Let's write benzene here, benzene, and toluene. So we have added all the required components. Now go to the fluid package, and click on add, and select the pyrolysis. Because hydrocarbons are involved, so we will use the pyrolysis equation of state as our thermal property model. The next step is to add the chemical reaction. So click on reactions, click on add, and add reaction. The first reaction is heterogeneous catalytic reaction. So add this reaction, and the side reactions are kinetic reactions. So add two kinetic reactions. So now we will enter the data of the reaction. So click reaction 1. So this is the first reaction where ethyl benzene is converted into styrene and hydrogen, and this is a reversible reaction. So ethylbenzene minus 1, that means it is reactant is converted into styrene, 1 mole styrene and 1 mole of hydrogen. And this base is partial pressure. The base company is ethylbenzene, and it is in reaction is happening in vapor phase. The base units are Pascal, and the rate units are kilomole per meter cube per second. Now we have to enter the rate, reaction rate. So this is, here we have to enter the data for the forward reaction. This is actually the rate of reaction. R1 is equal to K1 PEB. So K1 PEB is actually the forward reaction, while K1 by Ke PST PH2, this is the rate of reverse reaction. So first we enter the rate of forward reaction, K1 PEB. So K1 is given by this A1 exponential minus E1 by RT, and this is given by the value of A1, and this is the value of E1. So enter the value of A1 and E1. So this is a, and this is 158.6, sorry, 158.6 kilojoule per mole. Okay, now we have to enter the data for the reverse reaction, which is actually K1 by Ke PST PH2. So we defined this K1 by Ke as a K1 dash, which is given by this equation, and the value of this A1 dash and the value of A dash are given. So this is 4.511 exponential minus 9, and this is 34.34. So 4.511 exponential minus 9, and this is a 34.34 kilojoule per mole. Okay, so we have entered the forward reaction and the reverse reaction. Now this is actually the numerator of our equation. So you can see this is the numerator of the denominator. Now we have to enter the denominator as well. So if you click this kinetic help, it actually shows you how the rate is defined. So rate is numerator by denominator. Numerator is Ka basis. This is the forward reaction. This is the backward, the reverse reaction. We have defined. We already defined these two parameters. And the denominator is given as 1 plus K1 F1 basis plus K2 F2 basis, and so on. So this is actually the value of KST, and it is given as 1.3 exponential minus 4. Okay, and put this E0, and as in the denominator we only have the partial pressure of styrene, so just put 1 here because it is a PST. This is the partial pressure of the styrene. In the here it is given as PST power 1. So actually the exponent is 1, so we put 1 there, and we don't have anything else, hydrogen or the ethylbenzene, so we put exponents of those components as 0. Now close this and define the second reaction, reaction 2. Double click in the second reaction, ethylbenzene is converted into benzene and toluene. So 1 mole of ethylbenzene react and form 1 mole of benzene and 1 mole of the toluene. So this is partial pressure, the base is partial pressure, the base completes ethylbenzene, and this is vapor phase, and here this is given as 2.604 exponential minus 3, and this is 114.2. Sorry, this is 114.2 kilojoule per mole. Okay, so this reaction is defined, and it says it's not ready. That means that we have missed something. Okay, 1 mole of ethyl-benzene is converted into 1 mole of benzene and 1 mole of ethylene. Okay, so just delete this toluene. Okay, you can delete this toluene. Just click on press the delete button, it will be deleted. So 1 mole of ethyl-benzene form 1 mole of benzene and 1 mole of ethylene. You can see now that the balance is 0, and we are ready. Close this, and now click on third reaction, and here you have to define the third reaction where ethyl-benzene reacts with the hydrogen to form toluene and methane. So 1 mole of ethyl-benzene reacts with 1 mole minus 1 with 1 mole of hydrogen to form 1 mole of toluene, 1 mole of ethane. And you saw that the concentration, the rate of reaction was independent of the hydrogen concentration, so we will just put it 0 here. And here molar concentration, select the partial pressure, and the phase is oral. Sorry, this is the phase is vapor phase. Okay, and this A is given as a 7.116, and this is 208 kilojoule per mole. Okay, so you can see this is ready as well. And now just close this, and click on this add to PF, add to PF. So adds it to fluid package. Now we will go to the simulation environment. We will where we will construct our process flow diagram. So click on simulation, and go to view, click on model palette. When you click on simulation, normally this model palette is shown. However, if it is not shown, so you can click on view and then model palette. So this model palette will appear. Now click on the reactor, go to the plug flow reactor, install the plug flow reactor, and now double click on the plug flow reactor. So feed stream, and this is the feed stream and the product stream. Product. Okay, so it is asking for requires a reaction set. So go to reaction, okay, and reaction set 1, and now go to rating. The total volume is 5.655 meter cube, length is 4 meter, and there are 500 number of tubes, and the void fraction is 0.45. So now again go to reaction, and here you have to enter the catalyst data. So the particle diameter is 5 mm, so 5 exponential minus 3 meter, And now go to this uh, design parameters and use the organ equation to determine the pressure drop. Now go to the worksheet to specify the feed stream. So the temperature was 630 degrees C. The pressure was 138 kilopascal, 137.8 kilopascal, 137.8 kilopascal. And the composition of the stream was ethyl-benzene was okay, ethyl-benzene was 15 kilomole per hour. You have to select the mole flows here. Zero styrene, zero benzene, zero methane, zero hydrogen, zero toluene, and water flow rate was 150 kilomole per hour. And there is no ethylene. Click OK. So we have specified each and everything. Now wait for some time while the process is being simulated. So after a while this will turn into green. So the process is now simulated. Now so now click on the case study, click add, and find variable, plug flow reactor, go to the tube length, done. So this is the independent variable. We want to vary the tube length and study its effect on the dependent variable, which is the conversion. So find variable, plug flow reactor, and then go to the conversion, and done. Okay, now we are actually studying the uh, effect of length. We are actually studying the conversion along the tube length. So go to the case study and select sensitivity. Let's start from 1 up to 4 meter, and the step size is 0.5. Okay, and click on run. Here you can see the results, and you can also plot the results. So this is the conversion along the length of the tube. Okay, now go to the main flow sheet, double click on the plug flow reactor, and click on the performance condition. So it is showing us the temperature along the length of the reactor. It also showing the pressure, the vapor friction, and other properties as well. You can see this on plot, so just click on plot. Okay, you can see the pressure. The pressure is dropping from 137 to almost 121 along the reactor, and you can check the temperature as well. So this is the temperature plot. It is almost 592 up to 400 degrees C, up to 535 degrees C roundabout. You can also check the molar flows and the plot. So it is giving us the molar flow along the reactor. Similarly, you can check the mass flow, the volume, and the heat. Similarly, you can check the rate of reaction along the length of the reactor, the transport properties like viscosity, density, heat capacity. You can also see the composition along the length of the reactor, so ethyl-benzene, styrene, benzene, and so on. This is mole fraction. You can also see the molar flows. So this is in the molar flow in kilogram per hour along the length of the reactor, and you can see this in graph. So just click on this plot, and you can see mole fraction, mass fraction, liquid volume, or molar flow rates. Here select the component. So I'm ethyl benzene. I'm selecting ethyl benzene, then uh, styrene, okay, and then hydrogen, and ethylene, okay, yes, benzene. So this is the molar flow rate of the ethyl benzene. You can see that as we proceed through the reactor, so the number of moles of the ethyl benzene, they are dropping because of the conversion, and you can see that styrene and hydrogen and ethylene, they are increasing along the uh, length of reactor. Okay, now let us calculate the selectivity. So for selectivity, go to the again go to the model palette, and go to the manipulator, and add this spreadsheet. Double click on the spreadsheet, click on add import. So the selectivity is actually defined as mole of styrene product. That means that mole of desired product in the product stream, and mole of the reactant consumed. So it is mole of styrene in product divided by mole of ethyl benzene in feed minus moles of ethyl benzene in product multiplied by 100. So here go to the master component molar flow, select the ethyl benzene, okay, and now select product, and again the molar flow is ethyl benzene, and in the product select the molar flow of the styrene. Click done. So in cell A1 we have molar flow of ethyl benzene in the feed, and this is the cell A2 we have the molar flow of ethyl benzene in the product, and the molar flow of styrene in the product in the cell A3. Now go to the spreadsheet, and here I am entering the formula of the selectivity. This is equal to A3 divided by A1. A3 is the molar flow rate of styrene in product. A1 is the molar flow rate of ethyl benzene in feed. A1 minus A2, and steric 100. Okay, and I call this as a selectivity. Selectivity. Okay, so this is the selectivity. Selectivity is 96.11. Thank you very much.